So at this table, we have three different drugs. Now we have aspirin, sulfadimethoxam, and lidocaine. So aspirin and sulfadimethoxam are acidic drugs, while lidocaine is a basic drug. So as you can see here, the pKa of aspirin is equal to 3. Now, so at the pH of 3, the ionized or unionized form of aspirin is equal to 1. So when we are going to lower the pH of the environment to 2, as you can see here, there is an increase in the unionized form. When we are going to again lower the pH of the environment by 2, so meaning that we are going to lower the pH of the environment from 3 to 2, so there is a 100-fold increase in the unionized form. So that is the lipid-soluble form of the drug. So pH that is greater than the pKa of our aspirin would mean that there will be a more ionized or an ionized form. So when we, for example, going to increase the pH of the environment by 2, so that is 3, that is from 3, then we are going to make that 5. So there is also a tenfold increase now in the level of our ionized form. So a pH no greater than the pKa for an acidic drug would mean that we are going to increase the percent ionization or the proportion of the drug in its ionized form. pH that is lower than pKa would mean that for acidic drugs such as aspirin, we are going to increase the unionized form of the drug. So again, when we are going to review our ionized and the unionized form, so when we see ionized form, this is the proportion of the drug that is polar or water soluble, or it will not be able to cross the lipid bilayer. So for the unionized form, no, this is the proportion of the drug that will be absorbed, or this is the proportion of the drug that will be lipid soluble. In the case of sulfadimethoxam, it has a higher pKa level, no? So it has a pKa level of 6. So when we are going to put, for example, sulfadimethoxam in an acidic environment, no, from 1 to 5, so it will be absorbed, no, because the proportion of the unionized form of sulfadimethoxam is predominant at this pH level. So the lower the pH, so as you can see here, the lower the pH, the higher would be the unionized form. So at each pH level, so for example here from 5 to 4 to 3 to 2 to 1, there is also a tenfold increase in the level of the unionized form. The opposite is true when we are going to increase the pH now above the pKa. So for example, from 6 to 7, there will be a tenfold increase in the proportion of the ionized form. From 6 to 8, there will be a 100-fold increase in the proportion of the ionized form of sulfadimethoxam. For basic drugs such as lidocaine, so as you can see here, the pKa of lidocaine is at a pH of 3. So when we are going to decrease the pH, the ionized form of the drug will predominate. So as you can see here, from 3 to 2, so the ionized form here becomes 10, no? At 10 to 1, meaning that there are 10 ionized form for every an ionized form of lidocaine. So when we are going to decrease the pH below its pKa value, so we are going to also increase the ionized form. When we are going to increase the pH of our environment, so that would mean that there will also be an increase in the unionized form. So therefore, for basic drugs, increasing the pH of the basic drug would also increase the unionized form of our drug. So we have here an example, Loratadine. Now, Loratadine is an orally available drug. Now, it has a pKa value of 5. And we are going to answer this question. So where do you think the Loratadine will be absorbed? In the stomach with a pH of 2 or in the small intestine with a pH of 8? So for us to determine the ionization of our loratadine or the absorption of loratadine in stomach and the intestine, we must first determine whether that particular drug is a basic drug or an acidic drug. So loratadine, based on its chemical structure, is a weak base. It has a pKa value of 5, meaning that at a pH of 5, the ionized to unionized form of aspirin of loratadine will be equal to 1. So loratadine is an antihistaminic drug. So in the stomach, the stomach has a pH of 2. So that when we are going to compare the pH and the pKa of our loratadine, so the pH is equal to 2. So that pH refers to the pH of the stomach or the pH of the environment, while the pKa is an intrinsic property of our drug. So the pKa of our loratadine is equal to 5. So the difference between the pKa and the pH is equal to 3. So our pKa is 5. We are going to subtract that with our pH. pH is equal to 2. So as you can see here, our pH is less than our pKa. So since the difference is equal to 3, so our loratadine, which is a weak base, will be ionized in the stomach. So it will be more than 99% ionized in the stomach because when we are going to put a basic drug in an acidic environment, so that basic drug will be ionized. When we are going to put our basic drug in the intestine with a pH of 8, so as you can see here, the pH of the environment is more than the pKa. So our pH is 8 and our pKa is 5. So that would mean that for basic drug, when we are going to subject that into a basic environment, so that that basic drug would be unionized. So as we have discussed earlier, for basic drug, when we are going to increase the pH of our environment, so that would mean that we are going to increase the proportion of the unionized form. So the loratadine will be more than 99% unionized in our intestine. So since the difference is 3, so therefore loratadine will be a the proportion of our unionized to ionized form would be 1:1000. So meaning that there is a 1000 for every one ionized form of our loratadine, there are 1000 unionized forms. That is the ratio between the ionized and the unionized form of our loratadine in the intestine. So in this case, there are the ratio is again also 1:1000, meaning that the for every one an ionized form of loratadine, there are about 1000 form of our ionized form of our loratadine. So again, the predominant form here is ionized form because this is an acidic environment, and the predominant form here of our loratadine will be the unionized form because this is a basic environment. So basic, when we are going to put that to a basic environment, so that drug would be normally be absorbed. When we are going to put a basic drug to an acidic environment, so that drug will be trapped in that environment. So that is an example of the concept of our ion trapping. So therefore, now our loratadine will be better absorbed from the intestine, intestinal membrane, compared to our stomach. So we also have here another example of our weak acid drug, no, our aspirin. So in this diagram here, or in this example here, the pH of the stomach is given. So the pH of the stomach is 1.4 and the pH of the blood is 7.4. So of course 1.4 is very acidic, while the blood here, which is 7.4, is towards the basic side. So from our equation, we have here our equation of pH minus the pKa will be equal to the logarithm of our ionized form of our weak acid and the unionized form of our weak acid. So when we are going to compute for that, or when we are going to replace the value of our equation based on the given numbers, so we have here pH of the environment. For example, we are going to consider the pH of the blood. So we have 7.4. The pKa of aspirin is equal to 3.4. So this will be equal to 4. So the difference between 7.4 and 3.4 will be equal to 4. So the log of 10,000 will be equal to 4 in the blood. So we have here, the proportion of our, this one here is the ionized form because it has a charge, and this is the unionized form. So this will be equal to 10,000. So meaning that for every one an ionized form of aspirin in the blood, there are 10,000. Now 10,000 ionized form of aspirin in the blood. So the ionized form of aspirin is equal to 10,000-fold greater than the unionized form. So meaning that in the blood, with a pH of 7.4, aspirin is predominantly in its ionized form. So there are about 10,000-fold greater ionized form of aspirin in the blood compared to its unionized form. So for every an ionized form of aspirin, there are 10,000 ionized form. So this, how do we get the 10,000 here? This is because of the difference. The difference between our pH of the blood and our pKa. So the difference here is 4. So that is equivalent to a log of 4. The log of 4 here represents the 10,000. So there are 4 zeros here. That is equal to 4. So meaning that for a log base of 10, for example, we need to multiply 10 4 times in order to get our 10,000. So in the stomach, as you can see here, the predominant form of our aspirin in the stomach would be the unionized form. So as you can see here, we have 1 is to 0.01. So the unionized form of aspirin is equal to 1, and the ionized form of aspirin will be equal to 0.01. So again, the difference between our stomach pH, which is 1.4, and our pKa is equal to 2. So 3.4. So 3.4 minus 1.4. So that would be 2. pH. So pH is 1.4 here. Then our pKa is 3.4. That will be equal to -2. So pag negative again, so we are going to divide that, our number here, so that this will become 0.01, and our unionized form will be equal to 1 here. So meaning that mas marami yung ating unionized kaysa sa ating ionized. So dalawa, no? 2 yung difference nila. So our pKa is 3.4 and our pH is 1.4. So that will be -2. So meron ditong 2 places here, no? 2 zeros here, or 2 places here, no? To get the 1 here. So the difference is 2 decimal places. In the blood, the predominant form of aspirin will be the ionized, no, ionized form. So 10,000. So how do we get the 10,000? So we compute for our equation here, no. So pH is 7.4. We are going to subtract that with 3.4. So that is equal to 4. So 4 is equivalent to 10,000. So the log base 10 of 10,000 is equal to 4, meaning that we need to multiply 10 by 4 times in order to get 10,000. So since this is a positive, so multiply natin ito. Pag a negative naman yung ating value dito sa ating computation, so this would be, we are going to divide it, no? Kaya naging 0.01 siya dito. Dito naman, naging 10,000. So difference nila ay 4. 7.4 minus 3.4 is equal to 4, so 10,000. No? 4 zeros here. Predominant form will be the ionized form compared to the unionized form. So since mas marami yung ating ionized blood, so the aspirin will not be absorbed, no, in the blood, but it will stay, or it will be trapped in that particular compartment. So this slide here will also explain, no, the same. No? We also used here aspirin, which is a weak acid drug. So in the stomach, the aspirin will be unionized, so it will be absorbed. In the intestine, it will be ionized. So in the blood, the aspirin will be most ionized. So once aspirin moves from the stomach to the blood, it will be trapped in the blood, no, because it will be ionized in the blood. We also have here another example of our ion trapping here. This is an example of the effect of pH on the urinary excretion of our drug. So our example here is, this figure here is a mean cumulative urinary excretion of methamphetamine with an oral dose of 11 milligram in men as a function of the urine pH. So this experiment here evaluated, the effect of the pH to the urinary excretion of our methamphetamine. So this y-axis here represents the amount of methamphetamine that is excreted in the drug in milligrams. This x-axis here represents the time course. So this is 4 hours, 8 hours, and 12 hours. So methamphetamine is considered to be a weak base drug. And as you can see here, so it is a weak base drug. So when you are going to have an alkaline urine, so what happens is there is only a very low concentration or low amount of aspirin that will be excreted in the urine. So this represents here the amount of the urine that will be excreted when the urine is alkaline. So when the pH of the urine is alkalinized, so for example, there is, so in men, of course, the urine pH is usually acidic. But when we are going, for example, to administer or to ingest sodium bicarbonate, sodium bicarbonate is an alkalinizing agent. So it will alkalinize the urine. So for example, for methamphetamine, what happens in the alkaline urine is that there is only a very low amount of methamphetamine that will be excreted in the urine. So This is because now when we are going to alkalinize the urine, this will increase the percent of the unionized form of the methamphetamine. Now because methamphetamine is again a weak base drug. So pag ang weak base, ilalagay natin siya sa basic environment. So the predominant form of the drug will be unionized or lipid soluble. So when the drug will be lipid soluble, it will be absorbed in the body so that less amount of the drug will be available in the urine. So in this case, only about 1% of the drug will appear in the urine. So in contrast, when the urine is acidified, so for example, when we are going to acidify the urine and the urine reaches a pH of 4.9 to 5.3, this will happen, for example, by repetitive ingestion of our acidifying agent. Now, for example, we have ammonium chloride. So, repetitive administration or chronic administration of ammonium chloride, which is an acidifying agent, will acidify the urine. So, at this case, so as you can see here, there will be an increase in the excretion of the methamphetamine in the urine at an acidic urine. So this figure here reports that about 70% of the dose is recovered in the urine. So this means that when we are going to acidify the urine, a basic drug uh, will predominate. Now it will be converted into its ionized form. So it will become polar. It will become more water soluble. So it will be trapped in the urine. So when that particular drug will be trapped in the urine, so it's very easy for it to be excreted now in the urine. So therefore, when we are going to consider the principle of ion trapping, we can manipulate the pH of the urine in order for a particular drug to be excreted from the body. So for example, when there is a chronic administration of a particular basic drug, and in this case, for example, we have methamphetamine, in order for it to be easily excreted in the body, we can acidify the urine. Since our methamphetamine is a basic drug, so we can acidify the urine in order for it to be excreted in greater amounts in the urine. We also have here different examples of drugs based on the strength of their acidity and the strength of their basicity. And we also have here a comparison of the different drugs in terms of their pKa value and their absorption. So for example, we have here our very weak acid drug. This very weak acid drug has a pKa value of greater than 8. So example here we have pentobarbital. So it has a pKa value of greater than 8. So meaning that how would this affect its absorption? So a very weak acid drug with a pKa value of more than 8 will be unionized at all pH values. This since the drug now becomes unionized at most of the pH values, so it will be absorbed along the entire length of the GIT. So that will be the effect of the pKa and the property of the drug, their pH in terms of their absorption. We also have the moderately weak acid drugs such as aspirin and ibuprofen. It has a pKa value that ranges from 2.5 to 7.5. So this particular drug will be unionized in gastric pH and ionized in the intestinal pH. It has a better absorption. But of course, when we are going to compare that with a weak acid drug, so it has lesser absorption compared to our lesser absorption in different segments of the GIT. They are moderately weak acid drug, no, because of its pKa value, will only be absorbed better in the stomach, and it will not be absorbed readily in the intestine, no, because of its ionization. For drugs that are stronger acids with a pKa value of less than 2, so what will happen is it will be ionized at all pH levels. As we have discussed earlier, when we are going to, for example, when we lower the pH, or rather, when we are going to increase the pH of an acidic drug beyond its pKa value, so that would mean that there will be an increase in the ionization of our drug. So since there is an increase in ionization and we have here a very low pKa value, so it would mean that this particular drug will be ionized, meaning that when that particular drug is ionized, so there will be a poor absorption in the GIT. How about our very weak bases, now with a pKa value of less than 5? So these drugs will be unionized at all pH values, and they will be absorbed along the entire length of the GIT. So the renal excretion of drug will be affected by the pH of the urine. So excretion of some drugs will be affected by the pH of the urine. So this is an important concept of the ion trapping, or the pH partition hypothesis. So normally, for humans or for monogastric animals, the normal urine pH is about 5.3, and this is a slightly acidic pH. So the urine pH will vary from 4.5 to 8, and that will depend on the diet. Now, for example, meat decreases the urine pH. So when the diet, for example, is predominantly meat, the meat type, so the urine will be more acidic. And carbohydrate-rich food may increase the urinary pH. Again, most drugs are weak acid or weak bases, so the normal urine is about 5.3. It is slightly acidic and favors excretion of basic drugs. And most of the acidic drugs will be reabsorbed back into the body. So changing the pH of the urine can inhibit or enhance the passive tubular reabsorption of drugs. So for example here, the urinary pH trapping is important to enhance the renal clearance of drugs during toxicity. So for example, there is an amphetamine or gentamicin toxicity. So since these drugs are basic, so we can use an acidifying agent such as ammonium chloride in order to acidify the urine. So when we are going to acidify the urine, and there is a case of this basic drug toxicity, so what will happen is we are going to increase the ionization of this drug, so this will increase its excretion. We also have here another case of, for example, aspirin toxicity. Aspirin is an acidic drug. So in order for aspirin to be excreted from the body, we can alkalinize the urine by administering alkalinizing agents such as sodium bicarbonate. So we also have here another example of a weak acid drug overdose. So example of that is barbiturate. So barbiturate, which is a weak acid drug, will be when we are going to subject that in a acidic environment, so pH with a urine rather with a pH of 5.3, so that would be it will be more unionized in the urine and less ionized. In the blood here has a pH of 7.4. So what will happen for a weak acid drug in the urine is that it will be reabsorbed back in the body. It will be reabsorbed back in the body. so that less of barbiturate will be excreted in the urine. In the presence of the sodium bicarbonate, the urine is alkaline and more excretion of the acidic drug will happen in the urine. So for example here, we have here our urine and we have here the blood. So the blood here is a pH of 7.4. In the case of the toxicity with an acidic drug, so we can alkalinize the urine by again administering sodium bicarbonate. No, it is an alkalinizing agent. So when we are going to administer sodium bicarbonate, so we are also going to increase the pH of the urine. So this will enhance the ionization of our drug. So when there is a more ionized form of the drug, so this will increase the elimination or the excretion of our drug in the urine. We also have another example of ion trapping, and that is present in during pregnancy. So we have here the fetal blood. The fetal blood, now when we are going to compare that with the maternal blood, the fetal blood is slightly more acidic than the maternal blood, with a pH of about 0.1 unit less than the maternal blood pH. So the lower pH of the fetal blood facilitates the fetal uptake of drugs that are basic. So this is because, again, this is again an example of an ion trapping. No, because for drugs that are basic, they will be trapped in the acidic environment. So for example, usually during pregnancy, we administer local anesthetics. So local anesthetics are considered to be weak basic drug. So we also administer opioids. Opioids are analgesics or painkillers. So for example, when we are going to administer these weak basic drugs during pregnancy, particularly for example during labor, these drugs will be able to cross the placenta. Now, since the maternal blood is basic, it has more basic siya. So these drugs now will be able to cross the placenta in the non-ionized state. And when they reach the fetal circulation, they will become ionized. So again, they will become ionized because the fetal blood or the fetal circulation is acidic.